Hello everybody, welcome to the second day of Reunion Conference. Before starting, let me remind you that if you want to ask a question, you should use the button raise hand and we will allow you to talk. So our first speaker of today is Johannes Henn, and he will talk about the full angle dependence of the for-loop cusp anomalous dimension in QED. Please.
Thank you, Livia, for the introduction. Hi to everyone. Good morning to those in California. Good day to the rest. So this is work based on two papers, one very recent, just from last month, about the cusp anomalous dimension. And I was asked to somehow connect it to the KITP conference 3 years ago, which of course I have very fond memories of. But I did not remember what I talked about, so I looked it up, and there was this. This is one of the slides. So I was actually talking about scattering amplitudes in supersymmetric field theory, and specifically massive scattering amplitudes. So I was talking about some 4-particle amplitude, which depends on Mandelstam variables and the mass, and lots of things to say about those. In particular, they have really a host of interesting limits, which I tried to kind of summarize in this picture. And the connection to today's talk is that quite generally, if you think about special limits or certain physical effects in scattering amplitudes, then Wilson lines can be very important. And this was the case here in a Reggie limit. Importantly, there's some connections to integrability. So some of those n=4 superangular Wilson loops, they can be computed from integrability. I'll mention that later on also today. And also the second point here, high energy limits, so where you get rid of a mass and you just have mass scattering of massless particles. Those soft and infrared effects to a large extent are governed by Wilson lines and Wilson loops. So that's the connection. Today, I'm not going to talk about those massive amplitudes, but I'm going to talk more generally, also in a general field theoretic sense, in QCD, not just n=4, about Wilson loops. So here's the definition of a Wilson loop with a path-ordered exponential, and what determines whether or not, or to which physical phenomenon this is related to is the contour C. And I think a famous contour is that of having antiparallel lines, which is related to from which you can compute the quark-antiquark potential, just these Wilson lines representing static quarks. Then going to the topic of infrared divergences, if you have multiple Wilson lines emanating just from one point, and you can think of those lines representing the momenta of various particles, then that computes for you the vacuum expectation value that computes for you the bulk of the soft exchanges between those particles, and therefore tells you about the infrared divergences. And a special case, that I'll focus on today, is the one where you have two such lines. So then the contour just forms a cusp of a finite angle in general phi. So if you have massive particles, this angle is finite. For light-like particles, this angle goes to infinity. And so this is what we'll be focusing on today. But let me give you a bit more motivation before going into this. So in fact, the general case of multiple lines is actually very interesting, and there have been various signs of simplicity in the calculations. So first of all, let me just remind you, in the massless case, you can have in general these correlations between different particles, and it turns out that up to 2 loops, although there's more complicated diagrams, the formula is given by just a sum over correlations of 2 particles, so-called dipole formula. And for some time, people were speculating whether that holds true generally. That is not the case. There's a free loop correction which correlates 4 Wilson lines. So that's not quite as simple as it could have been. But on the other hand, this free loop formula, which was found by those authors here, is actually quite nice. It's structurally not too complicated. And in later work, the same authors, together with McLeod and White, even argued that under certain assumptions and putting in physics constraints, you could even bootstrap that formula. And so it's an interesting question how that continues at higher loops and what's the general structure of those soft anomalous dimensions. Now, much less is known in the massive case. So there basically we're at the 2-loop order, and there it turns out you have terms which go beyond dipoles also at 2 loops. Here's a representative diagram connecting 3 particles. And what's quite interesting to me here is that the calculation of even just this diagram is very complicated. But at the end of the day, the result is again relatively simple. You get some logarithms, some dilogarithms. There's some part of it factorizes. So it's quite intriguing. But this really comes out only at the end of the day. For instance, if you compute this in DIMREG, you get very complicated things, perhaps even elliptic functions. Only at the end of the day do you get this finite and simple answer. There's this more recent paper, well, from 2011, where an attempt is made to explain this. So they use some gauge where actually this diagram vanishes and only other diagrams contribute, but it's hard to go beyond the 2-loop order of this. So I think there's something interesting there, and to me this perhaps hints at other ways of computing these soft anomalous dimensions, which somehow circumvent these complicated intermediate stages. All right, so as I said, we're not going to compute those multi-leg soft anomalous dimensions, but we're going to focus on the 2-line case. I do want to say that this can give some insights also about the multi-line cases, in the sense that you can think of a 2-line case as a limiting, as the limit of those other ones. And therefore, whatever we discover, for example, as regards to the function space that appears in the 2-line case, will inform also these more complicated calculations. So specifically, if you had some conjecture about what the function space is in the multi-line case, so then that would tell you something about the 2-line case and vice versa. All right, so now let me focus from here on the cusp anomalous dimension for 2 lines. So there have been some interesting observations. So it turns out that a few years ago, in this paper, the free loop result was computed in general QCD. And so this means that one has one parameter, the number of fermions. And it turns out that there's a very simple pattern that describes all these matter-dependent terms. So roughly speaking, the NF-dependent terms, they could all be predicted from lower loop orders. There's some recursive pattern. Now, unfortunately, this pattern at 4 loops, it holds for some, but not for all color structures. Okay, and it's not really known why it holds in the first place and why it stops holding. So there's some mystery here. Now let me talk a bit more about those color structures. So up to 3 loops, the only color dependence you can get is just actually through these quadratic Casimirs of SUN. And then starting from 4 loops, there's also quartic Casimir terms, where basically you take the trace of 4 of the generators in some representation. And these, as you can see here, they appear like so. Where, for instance, this here we have the fundamental representation for the matter dependence in the loop, and some representation for your Wilson lines, if you wish. And so now, so these quartic Casimir terms are quite interesting because they appear for the first time at for loops. They also do not follow this pattern that they are given by lower loop terms. This was found in those papers here. And so we were just interested to know what they are and learn something in particular about what functional dependence they would have on the cusp angle. So this was the goal of the project, to focus at 4 loops on the quartic Casimir term and the one which is proportional to a either Fermion loop, or we also considered the case of a scalar loop. You'll see in a little while why that's interesting. All right, any questions at this stage about the setup and the goal? Okay, doesn't seem to be the case, so let me proceed. So this is the team. Robin is my former student from Mainz University. He graduated. He's now a postdoc at Siegen, and the rest is the team at Munich. My PhD student Christoph and postdoc Kai. So now we set out to compute those 4-loop quartic Casimir diagrams. Now the good news is there's actually only a handful of Feynman diagrams. It turns out that if you do a little bit of color algebra, you figure out that most of the diagrams are irrelevant, and we only have to worry about those 6. So we wrote down the Feynman diagrams in covariant gauge so that we later can check gauge independence. And we used some state-of-the-art programs for handling them, for doing integration by parts and integral reduction. Okay, so far so good. Now, of course, these are still complicated 4-loop diagrams, so we did have to work a little bit to get there. And in particular, for computing the functions, for computing the Feynman diagrams, we wanted to use the canonical differential equations method. But it turns out that here you have, for each integral family, you have hundreds, I think for this one of the order of 500 Feynman integrals. So clearly you want some degree of automation. And so in the course of the project, we decided to actually develop a new method, or to expand on previously existing methods to those authors, so that we could have this higher degree of automation. And roughly speaking, the idea is the following. So when you have integrals that have uniform transcendental weight, then, so if all of your, let's say 500 integrals have that property, then you get these simple canonical differential equations, and that's great. But in many situations, you may have only a shorter list. You have partial information, only some integrals that are UT, but you'd still like to use that information. And this is essentially what our algorithm provides. In fact, it only needs one UT integral, and then from that information, it deduces algorithmically the transformation to the canonical form. And then it's easy to compute the integrals. So now maybe for this audience, I said this is a general QED calculation, but I think it's amusing to mention that this one integral that you need, you could choose it to be the integral or some integral that's kind of naturally given to you from some n=4 Super-Mills considerations. So I find that quite amusing that in this sense, one n=4 integral, it gives you the information you need to compute all the QCD integrals. All right. So this turned out to be very useful to us, and of course it's more general than this particular project. So we put out a public algorithm so one can use this in many situations. And let me just illustrate that. I have kind of a benchmark slide here about this algorithm. So here, what you should take away from this slide basically is that the algorithm works well in situations for one kinematic variable as we have here, but also if there's several kinematic variables. So So there's these first 4 examples where there was 1 kinematic variable, but also those 5-point amplitudes where there's four different kinematic variables, and it's not a problem for the algorithm. And the other thing is that, and that was very important to us, it can handle large systems of equations. And so large in 2 senses. They can be large in the sense that you have many coupled integrals. So when you look at a cut of an integral, this is kind of the smallest basic block that you can have. And in this project of these Wilson line integrals, we had blocks of size 17, as in this sector here. And that typically is challenging, but it works quite well. You can see the timing here. So to bring this to canonical form just took 2 minutes, for instance. But then you have all these coupled blocks, and they naturally occur, inside of a bigger system. I just mentioned that it's in our case was something like 500 times 500, and that is also possible to run on on a typical computer. All right, so so we used this new tool in combination with other existing ideas in the literature, also notably a very useful program, although I believe that we programmed we implemented the key code ourselves, also this paper by Roman Lee, and also a number of other tricks for dealing with uniform weight functions. So then what we found is the following. I don't know if you can hear, but this is really tough work for my computer. I think it's overheating. You might hear the some ventilator in the background. But anyway, so at the end of all this hard work, we found for many integrals, we put them into this canonical form, like it's shown here. And the key information really is this alphabet, which is shown in the second line. So these, roughly speaking, correspond to different singularities of your functions, of your polylogarithms. And it's moderately complicated. Not only that, then there were some integral sectors where we almost, but not quite, found the canonical form. And this is an example. So this integral sector here, I think it initially has 11 integrals that are coupled. But we were able to, we studied, since it was more complicated than the others, we decided to study it in an expansion where epsilon goes to 0, because we want to extract some finite physical result. And then what it comes down to is this 2x2 system, where you see there's no more epsilon. So this is just for the finite integral, so to speak. And in order to put this into canonical form, we would have had to solve for these integrals G1 and G2. Now, we haven't done that. We suspect that this might contain some elliptic functions, so that you might find a canonical form, but it could be more complicated than what I've written up here. Now, the reason we didn't need to proceed further with this is that by looking at the degree of divergence of the integrals, we could look at what integrals we actually needed to compute the cusp anomalous dimension. And although we did have to deal with this sector, the integrals that are potentially elliptic, it turns out they do not contribute to the cusp anomalous dimension. So at the end of the day, having considered all of this, we can put together, we can compute all the integrals that we need for the cusp anomalous dimension, put it together, and we see that actually there's a number of cancellations. So in particular, we don't need this full alphabet, but it's only those 4 alphabet letters down here that appear in the final answer. And that is, of course, great news. It's actually almost as simple as the free loop answer, where we only had the first 3 of these letters. So now this 1 plus x squared is a new alphabet letter. All right. Now, so this is a long calculation. So let's see how the result looks, and let's see what we could do to make sure that it's actually the correct answer. So this new function b, so this matter-dependent Quoty-Casimir dependence, we we find that there's actually these 4 rational structures. And then the BI, those are polylogarithmic functions in the alphabet that I showed you. They have mixed transcendental weight going from 3 to all the way to 7. 7 is the maximal weight you would expect in such a calculation. Okay, why is it correct? What makes us think the answer is okay? As I told you, we computed in a general covariant gauge. The gauge parameter drops out. And then perhaps the most important checks have to do with this kinematic variable. So we have a 1 variable function, and it turns out there's 3 very interesting limits which had been considered previously. So we can check that in the small angle limit, in the massless limit, and in the antiparallel lines limit, we reproduce results from the literature. So in particular, in the massless limit, this checks the light-like cusp dimension, which had only been computed 1 year earlier and was in itself a quite complicated calculation. Interestingly, in the antiparallel lines limit, we make contact with the quark-antiquark potential, and so that checks this calculation by these authors from 2016. Now, since we have the full analytic formula, in each of the limits, we could produce also further terms, not just the ones that had been known, but also, if you wish, power-suppressed terms beyond the orders given in those references. I just show one particular result in the antiparallel lines limit, because there we find a surprising 0, which we don't know the reason for it, but I wanted to mention it. So if we parameterize the limit by this parameter delta, which tells you how far away you are from the antiparallel lines case, then the leading term is a pole which multiplies the quark-antiquark potential. And so now if we take our function b, we do indeed find this pole, and this whole combination here is the quark-antiquark potential computed previously. And so now what we find beyond that is that there's no order 1 term. The next term is actually order delta. And well, we don't know why that's the case, but it's quite curious. The same happens for the 1-loop formula, but if you look in the 2-loop and 3-loop QCD formulas, then there's no such vanishing. Then they do have order 1 terms. So we don't have an explanation. I just want to mention that there could be a connection, because this limit is also one that connects to physics of particles being produced near thresholds. So for instance, if you're interested in something like TT bar near threshold, this is a similar kinematic configuration. So this could be something interesting to look into in the future. So now we've computed this matter-dependent quartic Casimir. I think it's interesting to look at what's missing actually if we wanted to know the complete 4-loop QCD result. And turns out that there's only a few further color structures that are needed. So in my mind, perhaps the most interesting or most complicated is the gluonic quartic Casimir. Now, well, let me first say something about the other two. Assuming that you knew the gluonic quartic Casimir one, then one can show that the 2 remaining other color structures, although perhaps they don't look like so, they can be computed only requiring a planar calculation. And that's, of course, much simpler. And I would expect that these Feynman diagrams and the master integrals that we computed will be quite useful there. Okay, now what about the gluonic term? So this is the reason actually why we are interested also in the scalar contributions, because essentially now having the full matter dependence, meaning the fermions and the scalars, you can do something like a 1-loop supersymmetric decomposition. And what this means, so it might sound a bit strange because we're at 4 loops, but in some way these quartic Casimir terms, they appear for the first time, so it's a little bit like a 1-loop. calculation from that point of view. And so for that reason, it turns out that with our result, basically it's equivalent to know the n=4 answer for those terms, or just the pure glue answer. So this opens up a possibility to actually compute that remaining term by some nice supersymmetric calculation. Probably still a very complicated one, but it's, for what it's worth, that's what it gives you. So now another thing we can do, if we specialize from QCD to QED, so just take an abelian theory, then it turns out that we don't need all these CAs, and well, it turns out that actually we have all the terms that we need to assemble a full QED answer. So that's quite interesting. So let's have a quick look. So this is actually the full for loop result then for this quantity. So you can group the terms in a first term, which is just some function of the coupling. It's basically the light-like cusp anomalous dimension multiplied by the one loop formula, so one loop angular dependence, and then this new for loop term that we just computed. Okay, so we have this for loop function. Now I told you earlier that there had been some conjectures or some observations to up to 3 loops that that said that the NF dependence should basically be predicted by previous loop orders. And actually, had this conjecture been true, then this function B would have had to equal the function A. So now we know that's not the case, but it's still quite interesting to see how different are those two functions. We know they're rather different from functionally because you know, this is just a log, and I told you we have polylogarithms up to weight 7. But let's see how they behave if we evaluate them numerically. So now we plot those functions in different kinematic regimes. So for instance, let's look at this this first plot here. So on the horizontal axis, you have the this is actually the Minkowskian cusp angle, and we plot the function b. That's the solid line, and the dots represent essentially this one loop a one loop fit that was proposed earlier. And what you can see is that although the two functions certainly disagree, the shape is actually reproduced quite well, and even numerically in most of the range you have an agreement of roughly 10% or so. Maybe I should point out that that here at 0 the curves agree because there's analytically they vanish. And then at I think at large angle, that should correspond to the light-like limit. So there you see already some linear dependence that is analytically predicted. All right, so this is the region for Minkowskian angles. Then there's other regions for real angle, and with similar interpretation. Now on the right-hand side, there's two further plots. So if you analytically continue to negative x, that's then interesting if you view this as for instance, if you want to make contact to the quark-antiquark potential, or if you view this, as I mentioned earlier, as some process where you produce, for instance, top quarks and some further particles. In this case, the function can develop also an imaginary part, so that's why we plot imaginary and real parts over here. And here we don't plot the function b, but basically the difference between the function and the analytically continued function. And this again works quite well. You might worry what happened to the real part here. So in this case, the difference for the simple function, which is just a logarithm, that just vanishes, and that's why this approximation is just 0. But even so, if you look at if you actually compare this to the function b, then this is not farther, the error you make is not more than 25%. So, all right, to conclude here, it's in my mind, it's surprising how well this one loop approximation does qualitatively in reproducing the shape of this very complicated weight 7 for loop function. And well, we don't know what the reason for this is. So somehow just taking, and I should say what's this coefficient here? This is just the value of the light-like cusp anomalous dimension. So somehow it feels like if you choose as the effective coupling not G Young-Mills, but the light-like cusp anomalous dimension, that somehow by itself captures really a big chunk of the loop correction, it seems. All right. So now just a final slide before concluding. There's like a little bonus we were able to derive thanks to the calculation we did, and this has to do with the quark-antiquark potential. Remember that I told you that in general for these Corti-Casimir terms we can do a one-loop supersymmetric decomposition, and we computed all the matter dependence. Now it turns out for the quark-antiquark potential, these authors, they computed the gluon terms, and taking that and our result, we can put this together and then make a prediction for n equals 4 Young-Mills. And so specifically at the for loop order, this allows us to compute the non-planar terms in the n equals 4 quark-antiquark potential. And so putting together all these formulas, this is the prediction we get. Well, I hope this is interesting to people who study, for instance, integrability for Wilson lines. It's because this is, well, would be clearly a challenge to be reproduced by integrability methods. I don't think it's obvious because there's a number of things. This is actually for the bosonic Wilson loop. Most integrability applications have been done in those papers for the locally supersymmetric Wilson loop. But just 2 years ago, there was this paper by Correa et al. Where there's some hints that also the bosonic Wilson loop in n equals 4 Young-Mills might be integral. So perhaps there's something to do here. So with this, I'd like to conclude. So I showed you the full for loop result for the QED cusp anomalous dimension with the full angle dependence. We saw that curiously the result is qualitatively well described by a rescaled one loop function, where the rescaling is really the light-like cusp anomalous dimension, as if that was if you take that as an effective coupling, it captures most of the loop effects. Now going back to analytics, we identified the function space, and I argued that this could be quite interesting for bootstrap ideas for the soft anomalous dimension, because it clearly gives a constraint of what functions could arise more generally if you look at the 3-line or the 4-line case. And also, as you could see in the calculation, and I think also in some previous calculations of the soft anomalous dimension matrix, the intermediate results that we had were much more complicated than the final answer. And I think this at least it motivates me to look for some better ways of computing the answer, perhaps exploiting more of the physics, exploiting the fact that we're computing a well-defined finite quantity and not some arbitrarily high orders in dimensional regularization. Thank you very much.
Thank you, Johannes, for this very nice talk. Now we have time for questions. So please I would like to remind you to use the raise hand button.
I would like to ask a question. I cannot raise the hand.
Yeah.
So in the formula for gamma alpha that you showed a few slides ago, yes, this one. Now, well, there is if you look at the transcendentality weights of these numbers, for example, these terms nf square and nf cube in the alpha to the 4, they don't have zeta 5. Do you think it means something? Obviously, there is no uniform transcendentality or anything like that, but do you think some weights are excluded at certain orders, or can you read off some rules, or is it just kind of a low loop order accident, all these things?
Good. Yeah, I certainly can't read off some rules, but I do think that it means something. I just can't tell you what it means. But let me be a bit more specific. There was something that was quite interesting to us. So we're talking now about the transcendent weights here, and maybe we can just, if we focus on the zeta 5 that you mentioned, and we multiply with this log, we see this is weight 6, right? So if we count together everything, there's also, from a Feynman diagram, there's a 1 over epsilon, the overall divergence that multiplies this. So this gives weight 7 in total, and it's a 4-loop calculation. So now you know that, of course, the maximal weight that we expect from a 4-loop calculation is 8. So you could say, well, there's something interesting. This is less than maximal weight. And this is something that has been observed for these matter-dependent terms in the light cusp dimension. So when we started out this project, we weren't sure, of course, but we entertained the possibility that this function b might not have maximal weight 7, but only some lower weight terms, which would have simplified our life for sure. This did not happen. So this is I think this is interesting. There's actually some genuine weight 7 terms here in the matter-dependent terms of the cusp dimension. If you take the light-like limit, those terms somehow they disappear. But so this is an example, not the first example. There's other cases for scattering amplitudes where, so if you think in terms of maximal transcendentality principle, is it true that the n=4 result has all, if you look at the maximal transcendental terms, that's equal to the result in some other theories. So here it's not the case, and so that's something one can point out in this area.
But can you, for example, here looking at your 4-loop result, if you look at the coefficients in front of nf square, and nf cube, like deeper you go in nf, the transcendentality kind of falls. You have
exactly. That's kind of what I was referring to. So you kind of, roughly speaking, you hope that the more nfs you have, the simpler it gets. But what I'm saying is that at least at the level of our calculation, it did not seem that we benefited from any special simplicity.
Thank you.
More questions? Actually, I have one. You briefly also comment on this in the conclusion, but maybe you can elaborate a bit more. So you have diagrams which are potentially elliptic, right? But then the final answer, I mean, they disappear. It's just polylogarithms. Do you have any idea why? Is there some deep reason, do you think, or they just...
Yeah, I do think so, but now we're getting, of course, into the realm of speculation, but I mean, I'm very happy to do so. I really think that this is meaningful, that there's better ways of doing this calculation. And maybe I can just give an analogy of, maybe it's also not something that's so well known, but let me just mention it. So I did mention also this soft downward dimension matrix for massive particles, which now has been computed already over 10 years ago. And well, I also tried a little bit. And so I think this is also a case where if one just uses dimreg on, for instance, this integral here, things get extremely complicated, much more complicated than they have to be, in my opinion, including elliptic functions. And I think this is an artifact of the regularization. So it's possible. So here we have actually an advantage because we're computing very physical things. We know exactly where the divergences come from. To some extent, we can even take care of them before starting the calculation. Often it's not done because dimensional regularization is so convenient. So we kind of live with that often what's a little inconvenience of computing more than we need, and then we throw it away in the end. But there's cases like this one where I think it's actually makes life much more complicated. And so in this particular example, there's ways of choosing different regulators which allow you to perform the calculation, but circumventing all these more complicated functions.
Okay.
And so I hope that's a more general lesson that we can take.
Okay, so it's a resolve methods, really.
It's a question of methods, and to me, that's my personal interpretation. It's that dimensional regularization is perhaps not the most natural when it comes to extracting those physical four-dimensional results.
Thank you. Lance has a question.
Hi, thanks for that talk, Johannes. I have a number theoretic question like Yara, but I would like to look at the quark-anti-quark potential limit, where you have a Li4 of a half. You might notice that you also have a log to the fourth of 2 next to it, and they both have a, let's see, I think there was another slide. Yes. Where you had Li4, that was in the n=4 version, I think.
So that's later on.
Yeah.
Oh yeah, there it is. Yes, indeed.
Thank you. So interestingly, there's a 34 in front of that, and there's a 17 in front of the log 2 to the 4th term. The ratio between the two is 1/24. And this same ratio shows up in the electron anomalous magnetic moment, I believe. I think it would be interesting to compare in more detail the kinds of numbers you get in that context to this one. And you generally have a pi squared in front of everything here. And that's slightly unusual in the sense that the electron anomalous magnetic moment hates naked log 2s. It does have pi squared log 2, which is what you have too. But it does have the Li4 without the pi squared in front of it. Anyway, you might be interested to see if there's any information you can glean by taking the coaction on these numbers. But you don't have as much lower loop stuff to play with because this is kind of a new structure. That's all.
Yeah. Thanks a lot for making this comment, Lance. This is I find this really interesting. But about the first part, we do the Li4. It ultimately comes from the gluon terms from this reference by Steinhauser et al. And they do group the Li4s with the log to the 4s in a particular way. So I suspect that's due to me unexpanding that kind of makes it look like it is here. But yeah, and thanks very much for this connection to the magnetic moment. That's definitely something I haven't looked into yet.
Okay, I think we can proceed to the second speaker. Let's thank Johannes again